The universe is actively rewriting our definition of a habitable world. For generations, the hunt for another Earth focused on a simple formula: find a rocky planet orbiting in the Goldilocks zone, where temperatures are just right for liquid water. But the cosmos has a far more creative imagination than we do. Astronomers are now discovering worlds that sit perfectly in that temperate orbital band, yet resemble nothing like our home. Some may have global oceans of lava under skies thick enough to crush mountains. Others might be locked in place, with one side in perpetual scorching daylight and the other in endless frozen night. By the end of this exploration, you will see our pale blue dot not as a universal standard, but as one single possibility in a vast gallery of living worlds. How could biology take hold on a planet with no solid surface or beneath a hydrogen sky? What does it mean for a world to be Earth-like if it challenges every assumption we have? The search for life is expanding into realms once confined to science fiction, and it forces a profound question. When you think of home, how far are you willing to stretch your imagination? That narrow band of orbital real estate we call the habitable zone offers a comforting promise. It suggests a place of balance where a world receives just enough stellar warmth to cradle liquid water without boiling it away into space. For decades, this idea of a Goldilocks zone, not too hot and not too cold, has been the cornerstone of our search. Yet this framework is built on a single, powerful assumption. It assumes that every planet in that zone will be, at its heart, a version of Earth. We have been searching for a mirror, only to find that the universe specializes in kaleidoscopes. The truth is, orbital distance is merely the first line on a very long checklist. Think of it like real estate on Earth. Two houses might sit on the same sunny street, but one could have a sturdy roof, good plumbing, and a breathable atmosphere inside, while the other is missing its walls, filled with toxic gas, and has no protection from solar storms. Their address is the same, but their potential for supporting life could not be more different. A planet's atmosphere acts as a global temperature regulator and a protective shield. A world like Venus, for instance, orbits near the inner edge of our own sun's habitable zone, but its thick carbon dioxide atmosphere creates a runaway greenhouse effect, turning its surface into a furnace hot enough to melt lead. Its location suggested potential, but its atmosphere dictated a very different fate. Then there is the star itself. Our sun is a relatively stable, long-lived yellow dwarf. But many stars in the galaxy are red dwarfs, smaller, cooler, and far more temperamental. A planet would need to orbit much closer to such a star to stay warm enough for liquid water, well within what we would consider the habitable zone. But at that intimate distance, the world becomes locked by tidal forces, one face permanently pointed toward its sun, the other toward the eternal dark of space. This creates a planet of extremes, a study in contrasts where the concept of a global, temperate climate simply does not apply. Furthermore, red dwarfs are prone to violent flares, bathing their close-orbiting planets in intense radiation that could strip away atmospheres and sterilize surfaces. So a planet can be perfectly positioned for warmth, yet exist in a stellar environment that is inherently hostile. Even geology plays a decisive role. A planet's internal heat engine, driven by radioactive decay and residual formation energy, fuels volcanic activity and the movement of tectonic plates. This churning is not just for dramatic landscapes, it is a planetary recycling program. It regulates atmospheric gases, cycles minerals essential for life, and helps maintain a global magnetic field. That magnetic field is perhaps the most invisible yet critical guardian of habitability. It deflects the relentless stream of charged particles from the star, the solar wind, which would otherwise slowly but surely erode the atmosphere away into space. A planet could have a thick, promising atmosphere and a perfect orbit, but without this magnetic shield, it may be slowly bleeding its life-supporting blanket into the void. So the old checklist is obsolete. Finding a rocky world in the habitable zone is no longer the finish line, it is the starting gate. It tells us the planet has won the orbital lottery, but the real game of survival has only just begun. The question shifts from, is this world in the right place, to what is this world actually made of, and what story does its chemistry, its geology, and its star tell about its true potential? This brings us to our first profound challenge, the Super-Earth Conundrum. Meet Kepler 22b, a world discovered orbiting comfortably within its star's habitable zone. It is not a gas giant like Jupiter, nor a small rocky world like Mars. Kepler 22b is something entirely different, a planet with a radius over twice that of Earth. It represents a class of worlds our own solar system does not possess, and they are rewriting the rules of planetary science. A super-Earth is not simply a bigger version of home, it is a distinct category of planet, and its sheer size creates an environment of extremes. The most immediate consequence is gravity. On a world with several times Earth's mass, the pull at the surface would be significantly stronger. This immense gravity does more than just make you feel heavier, it fundamentally reshapes the entire planet. It can pull and hold onto an atmosphere of staggering density and depth. Imagine an ocean of air. The sky on such a world would not be a thin, breathable veil, but a thick, oppressive blanket. Surface pressures could be hundreds of times greater than what we experience, pressures that would crush most machinery and alter the very nature of chemistry. Under such a crushing sky, the geology itself becomes alien. The familiar cycle of plate tectonics, with continents drifting on a molten mantle, might not operate at all. Instead, the entire surface could be a single, unbroken expanse, perhaps a global ocean of water under that immense pressure, or a landscape of exotic, high-pressure forms of rock and crystal that do not exist on our planet. Continents as we know them might never form. This presents a fascinating puzzle for astrobiologists. If the surface is a hostile, high-pressure realm, where could life gain a foothold? One possibility lies in the atmosphere itself. In that deep, dense air, layers might exist where temperatures and pressures are just right for complex chemistry to occur. Could buoyant, balloon-like organisms float eternally in those thick skies, harvesting energy from the dim starlight filtering through the haze? Or perhaps life would retreat from the crushing surface entirely, finding sanctuary deep within the planet's crust, in subsurface oceans insulated by miles of rock, where the pressure from the world above is balanced by the surrounding stone. The existence of super-Earths like Kepler 22b forces a radical expansion of our imagination. It compels us to consider biologies that do not rely on a thin, Earth-like atmosphere or a familiar rocky shoreline. These worlds challenge the very foundation of what we consider a habitable environment, pushing the boundaries of life into realms of immense pressure and profound gravity, proving that the universe's recipe for a living world may come in sizes and forms we are only beginning to comprehend. But gravity is not the only force that can sculpt an alien Earth. Consider a world that has surrendered its spin, a planet caught in a cosmic embrace so tight it can no longer turn. This is the fate of many worlds orbiting the cool, faint red dwarf stars that dominate our galaxy. To orbit within the habitable zone of such a dim star, a planet must huddle incredibly close. At that intimate distance, the star's gravitational pull becomes a brake, slowing the planet's rotation until one face is permanently locked toward the light, and the other is condemned to an eternal frozen night. You are left with a world of absolute extremes, a hemisphere of relentless, scorching daylight, and a hemisphere of deep, space-cold darkness. the very idea of a global, temperate climate evaporates. Yet within this stark division, astronomers see the ghostly outline of a possible habitat, a scenario so strange it has earned a vivid name, the eyeball Earth. Imagine standing on the Terminator line, the razor's edge between perpetual day and endless night. Underfoot, the ground might be temperate. Before you, stretching into the distance, lies a vast, sun-blasted desert where any water has long since boiled away. Behind you, the land gives way to a frozen wasteland where the atmosphere itself might freeze and fall as snow. But right at this twilight border, where the star forever hangs low on the horizon, a miraculous balance could be struck. Here, the energy from the star could be just enough to melt ice, but not so much as to vaporize it. The result could be a planet-girdling ring of liquid water, a single, narrow ocean encircling the globe like a blue iris around a dark pupil, hence the name Eyeball Earth. This is not an ocean as we know it, with waves crashing on distributed continents. It is a liquid ribbon, a habitat confined to a single, stable band of twilight. Life in such a place would face challenges beyond our earthly experience. The extreme temperature difference between the blazing day side and the frigid night side would fuel permanent, hurricane-force winds roaring from the hot hemisphere to the cold one, a relentless atmospheric river scouring the landscape. Any organism relying on sunlight for energy would have a unique problem. The sun never rises or sets, it simply sits unmoving in the sky. Photosynthetic life might evolve to slowly track its arc across the horizon, or it might flourish only in the shallow waters where the light penetrates at just the right angle. The entire ecosystem would be compressed into this one narrow band, a bustling, crowded metropolis of biology sandwiched between two sterile deserts. The existence of such worlds forces a profound shift in our thinking. It dismantles the assumption that a planet needs a regular day-night cycle to be habitable. It suggests that life is not a global phenomenon but can be a local one thriving in a permanent, fragile twilight, proving that habitability can be a condition of a place rather than the condition of an entire world. Yet even a world of eternal twilight might seem familiar compared to the next possibility, a realm where the very sky is a different element. Astronomers have recently proposed a stunning new class of habitable world, one that sounds like it was pulled from the pages of the most imaginative science fiction, the Hycean planet. Picture a world significantly larger than Earth, a water-rich sphere swaddled in a thick, hydrogen-rich atmosphere. From a distance, it might resemble a steamy, shrouded marble. On its surface, temperatures could be scorching, a direct result of that dense atmospheric blanket trapping heat. But here is where the hypothesis turns everything we know about habitability on its head. Beneath that crushing sky, the immense pressure could create conditions where water cannot boil, no matter how much heat is applied. Instead of a surface of steam and vapor, the entire planet could be cloaked in a single, global, planet-wide ocean, a deep, dark abyss kept in a perpetual liquid state. This transforms our search completely. In the sunless depths of that warm, global ocean, life would not rely on the faint light of a distant star. Instead, biology could be fueled by chemical energy, perhaps from hydrothermal vents on the ocean floor, similar to the thriving ecosystems we find in Earth's deepest trenches, or from complex reactions between the ocean and the hydrogen-rich atmosphere above. The entire concept of a surface of continents and shorelines becomes irrelevant. Habitability is pushed deep into the planetary interior, into a realm of permanent pressure and darkness. This idea also dramatically expands the map of where we might look. That thick hydrogen atmosphere acts as a superb insulator, trapping internal heat and preventing the ocean from freezing solid. This means a Hycean world could maintain its liquid ocean far from its star, well outside the traditional boundaries of the habitable zone, in regions we once considered far too cold for any hope of life. A planet orbiting in the chilly outskirts of its solar system, once written off as a frozen wasteland, could secretly harbor a vast, warm sea beneath a frozen crust of ice and a sky of hydrogen. It forces us to abandon the deeply ingrained idea that life requires a rocky surface to crawl onto, or a nitrogen-oxygen atmosphere to breathe. Instead, it points to the vast, hidden abysses of other worlds as the most likely cradles for alien biology, suggesting that the most common homes for life in the cosmos might be places we cannot see and can only infer dark oceans waiting beneath alien skies. There is another, more turbulent path a world might take. Volcanic fury is not confined to the scorching realms close to a star. A planet can orbit at a perfectly temperate distance and still be a cauldron of geological violence, its habitability born not from calm but from relentless upheaval. This is the lava world paradox. We once assumed that for a world to be life-friendly, it needed a certain geological stability, a gentle churn of plate tectonics to recycle materials without constant catastrophe. But the cosmos has a different blueprint in mind. Consider a world not unlike Jupiter's moon Io, but scaled up to planetary size and placed gently within a star's habitable zone. Io is the most volcanically active body in our solar system, not because it is close to the Sun, but because of the immense gravitational tug of war between Jupiter and its other large moons. This tidal heating stretches and squeezes Io's interior, generating enough friction to melt rock and fuel its spectacular, constant eruptions. Now, transplant that same ferocious energy source to an Earth-sized world in the temperate orbital band. The heat to power its volcanoes would not come from its star, but from the gravitational dance with neighboring giant planets or large moons. The result would be a world with a deceptively calm address. From a distance, it sits in the Goldilocks zone, but on its surface, the thin crust might be a global patchwork of fresh lava flows, volcanic plumes, and fissures venting heat and gases into the sky. The atmosphere would be a thick, hazy shroud rich in carbon dioxide, sulfur dioxide, and water vapor, belched forth from countless eruptions. This very volcanic outgassing could create a powerful greenhouse effect, trapping just enough stellar warmth to allow for liquid water to exist in pockets, perhaps in cooler highland regions or within vast steam-filled calderas. It is a vision of a habitable zone utterly redefined, not as a place of balance, but as a theater of permanent geological drama. For life, such a world presents a stark dichotomy of danger and opportunity. The surface would be a hazardous landscape of shifting ground, toxic gases, and searing heat. Yet, beneath that unstable crust, vast networks of aquifers could be heated by this relentless geothermal energy. These subsurface oceans, insulated by kilometers of rock, could provide stable, warm, and mineral-rich environments, isolated from the chaos above. Or life might not hide at all, but adapt to thrive in the chaos itself. Biologists on Earth have found extremophiles thriving in boiling acidic hot springs and within deep-sea hydrothermal vents, ecosystems that run on chemical energy from the planet's interior, completely independent of sunlight. On a volcanic habitable world, biology might evolve to use sulfur or iron as its energy currency, with the planet's endless eruptions acting not as an apocalypse, but as a continuous, life-giving delivery system of raw materials and warmth. This possibility dismantles another core assumption, that a living world must be a quiet one. It suggests that the line between a sterilizing inferno and a nurturing cradle can be astonishingly thin, dictated not by location alone, but by the hidden, churning heartbeat of the planet itself. But what if the very idea of a surface is an illusion? Our final, and perhaps most ethereal, challenge to Earth-like norms comes not from a solid world, but from a cosmic puff of gas. Astronomers have identified a strange class of planets known as mini-Neptunes, worlds with masses several times that of Earth, yet densities so astonishingly low they have been compared to marshmallows or spun sugar. These are not compact, rocky spheres, but puffy giants enveloped in vast, distended atmospheres of hydrogen and helium that stretch for thousands of miles. Now place one of these tenuous giants gently into the habitable zone of its star. It possesses no solid ground, no continental shelf, no ocean floor in any traditional sense. Yet within its deep, layered skies, a hidden habitat could await. As you descend from the cold outer haze into the deeper atmosphere, pressure and temperature gradually increase. At a certain specific altitude, a magical boundary could be crossed, a layer where the conditions are just right for water to exist not as ice or vapor, but as liquid droplets. This would create a permanent, global band of cloud, a temperate aerial ocean suspended in the sky. In this stable zone, freed from the need for any solid foundation, an entirely aerial biosphere could, in theory, take hold. Picture microscopic life not sinking but floating, buoyed by the thick atmosphere. More complex forms could evolve balloon-like structures filled with lighter-than-air gases, allowing them to drift perpetually within this nourishing layer. They might harvest energy from the filtered starlight above, or from the complex chemical reactions occurring within the atmospheric soup itself, a metabolism based on alien chemistry. This is the Puffy planet enigma, and it represents the ultimate decoupling of life from land. It proposes that an entire living world could be a sky, a stable atmospheric stratum where biology blooms without ever touching down. It challenges the most foundational Earth-centric view of all, that life must be grounded, that it requires something to push against, to grow upon, to root into. Instead, it offers a vision of existence as something fluid and floating, a permanent resident of the golden hour, forever adrift in the gentle currents of an eternal, habitable sky. The story of a world is written not just by its orbit, but by the character of its sun. Our own star is a steady, reliable presence, a yellow dwarf providing a consistent glow for billions of years. Yet this stellar personality is the exception, not the rule. The most common stars in our galaxy are the red dwarfs, small, cool, and often temperamental. To bask in enough warmth for liquid water, a planet must orbit incredibly close to such a faint star, well within the distance Mercury circles our Sun. This intimate dance comes with a perilous trade-off. Red dwarfs are notorious for their violent outbursts, erupting with flares that can double their brightness in minutes and hurling colossal clouds of charged particles, coronal mass ejections, directly at their orbiting world. For a planet snuggled in that tight habitable zone, these events are not distant astronomical phenomena, they are existential weather. A single powerful flare could bathe the entire dayside in a torrent of X-rays and ultraviolet radiation, while a coronal mass ejection could slam into the planet's magnetic field, potentially shredding its atmosphere over time. This stellar fury adds a brutal new filter to the search for life. A planet could have a perfect orbit, plentiful water, and a promising chemistry, but if its star is constantly lashing it with radiation, any fragile beginnings on the surface could be repeatedly scoured away. Survival in such a neighborhood demands extraordinary planetary defenses. A powerful global magnetic field, like Earth's, could act as a shield, deflecting the worst of the stellar wind and protecting the atmosphere from being stripped. Alternatively, a world with an exceptionally thick atmosphere might absorb and dissipate the incoming energy high above the surface. Or perhaps life simply avoids the surface altogether, retreating into the safety of a global ocean or a labyrinth of subsurface caves, using kilometers of rock or water as a natural radiation shelter. In a red dwarf system, the most Earth-like planet might be one where nothing lives on the Earth-like surface at all. This realization shifts our gaze to another stellar class, the orange K dwarf stars. Slightly cooler and smaller than our Sun, but larger and more stable than red dwarfs, these stars offer a compelling possibility. They burn their fuel more slowly, granting them lifespans tens of billions of years longer than our suns, and they exhibit far less of the violent flaring activity. A planet in the habitable zone of a gentle K-dwarf star might enjoy a more stable, more enduring radiant glow than Earth has ever known. Its biosphere would have eons more time to develop complexity, free from the constant threat of stellar tantrums. The temperament of the star, therefore, becomes a decisive author of planetary fate. It forces us to listen to the silence between the flares, to measure not just the amount of light, but its quality and consistency. A world's potential is now a conversation between its geology, its atmosphere, and the very personality of the star it calls home. Earth's familiar blue sky is a biological signature, a breathable artifact of its own unique history. But swap out that nitrogen and oxygen for a different atmospheric recipe, and the entire concept of a habitable zone becomes fluid, a matter of chemical alchemy. An exoplanet's sky is its climate control system, and the ingredients available in the cosmic kitchen are far more varied than our own. A world with a thick blanket of carbon dioxide, for instance, experiences a supercharged greenhouse effect. That dense atmosphere traps infrared radiation with incredible efficiency, acting like a planetary heating pad. This means a planet orbiting farther from its star, in a region we would traditionally label as too cold, could be warmed to temperate conditions solely by the chemistry of its own air. It turns a frigid, outer solar system orbit into a potentially balmy one, dramatically redrawing the map of where life could exist. Conversely, a world with a different mix might reflect more sunlight, cooling a planet that sits closer to its star. The habitable zone is not a fixed ring around a star. It is a shimmering, shifting band whose boundaries are painted by the colors of an alien sky. Some of those colors could be profoundly strange. A methane-rich atmosphere, for example, does not simply trap heat. It interacts with starlight in complex ways, potentially creating thick, orange organic hazes that permanently shroud the planet. This haze could cool the surface by blocking sunlight, or it could create warming layers at higher altitudes, presenting climate models with puzzles we are only beginning to solve. And then there are the tantalizing hints of biology itself, the biosignatures. On Earth, the simultaneous presence of oxygen and methane in our atmosphere is a chemical paradox, a dynamic imbalance that is continuously replenished by life. Finding that same unstable combination in the air of another world would be a monumental discovery, yet the universe is a master of inorganic chemistry. Geological processes like serpentinization, where water reacts with certain rocks, can produce hydrogen and methane. Photochemical reactions in a planet's upper atmosphere can generate oxygen from water vapor, even in the complete absence of life. What looks from a distance like a sure sign of a living world could just as easily be the signature of a complex, sterile geochemical cycle. This is the exquisite challenge and promise of atmospheric spectroscopy, our window into these distant skies. When an exoplanet passes in front of its star, a tiny fraction of the starlight filters through the planet's thin atmospheric rim. Different gases in that air absorb specific wavelengths of that light, leaving dark lines in the spectrum like a chemical barcode. We are learning to read these barcodes from across the galaxy, each one a story written in light and shadow. Every new spectrum is a confrontation with our assumptions, forcing us to ask not just whether a world is Earth-like, but what new definition of Earth-like the universe is presenting to us today. The true habitability of a planet is not written in its orbit alone, but in the subtle, complex chemistry of its alien air. Our search for life has been anchored by one profound, earth-bound truth: water is the universal solvent. Its unique properties make it a master of chemistry, dissolving salts, transporting nutrients, and shaping the very molecules of our biology. But this conviction, while powerful, may be the ultimate form of planetary bias. What if life elsewhere never learned to swim? The cosmos is a vast laboratory filled with alternative ingredients, and on worlds far colder or hotter than our own, the rivers that flow may be made of something else entirely. Saturn's largest moon, Titan, offers a stunning preview. Far from the sun's warmth, its surface is sculpted by flowing rivers and dotted with vast seas, but they are not filled with water. These are reservoirs of liquid methane and ethane, hydrocarbons that exist as gases here on Earth but flow like water in Titan's deep freeze. In such a frigid ocean, chemistry operates at a glacial pace. Reactions that would be explosive on our world unfold with a slow, deliberate patience. Could a form of biology emerge here, one not built on the frantic dance of carbon in water, but on the methodical, cryogenic assembly of complex molecules in a methane bath? The molecules of life would need to be sturdier, their bonds designed for stability in the cold. Metabolism would be achingly slow, perhaps playing out over seasons that last for decades. It is a vision of life not as a flame, but as a slow-burning ember, thriving in a landscape we would perceive as a frozen, alien wasteland. At the opposite extreme, consider a world closer to its star where temperatures soar. Here, water would have boiled away eons ago, but other liquids could take its place. Dense clouds of sulfuric acid might rain from the sky, pooling in basins to form corrosive seas. In such a caustic environment, a solvent like sulfuric acid could facilitate a radically different set of biochemical reactions, ones based on sulfur cycles instead of our carbon-based norm. Or, under immense pressure, carbon dioxide itself could enter a supercritical state, a fluid phase that is neither quite a liquid nor a gas, possessing remarkable solvent properties. In this churning, dense medium, life might find a way to structure itself, building membranes from silicon-based compounds instead of fragile carbon chains, creating biology that is literally rock solid. This expansion of possibility shatters the foundational pillar of the traditional habitable zone, the requirement for liquid water. It suggests that the zone itself is not a fixed region, but a spectrum that shifts with every possible solvent. A methane habitable zone would exist much farther from a star, in the realm of the ice giants. An ammonia habitable zone might lie somewhere in between. By clinging to water as the only viable medium, we risk turning our telescopes away from the most alien and wondrous biospheres of all. The universe's recipe for life may call for ingredients we have barely begun to consider, mixing them in oceans we cannot yet imagine, proving that the chemistry of life is limited only by the boundless creativity of the cosmos itself. Our own planetary stability is a gift from the cosmos, a delicate arrangement of celestial partners. Earth does not stand alone. The gentle, consistent tug of our large moon acts as a gravitational gyroscope, steadying the tilt of our planet's axis over immense timescales. Without that lunar anchor, Earth's tilt could wander chaotically, shifting from nearly upright to drastically angled over thousands of years. The consequences would be catastrophic, turning our predictable seasons into a global roller coaster of climate extremes, where ice ages and scorching droughts could alternate across the same latitudes in geological blinks of an eye. A planet's axial stability is a silent prerequisite for the long, uninterrupted evolution of complex life, and it is a condition often written not by the planet itself, but by the moons that orbit it. A world in the habitable zone lacking a sizable lunar companion might be a beautiful, water-rich sphere, yet one condemned to a future of unpredictable, violent climate chaos, its potential for a stable biosphere undermined by a fundamental lack of celestial balance. Beyond our moon, another giant plays a guardian role in our solar system's architecture. Jupiter, with its immense gravity, acts as a cosmic vacuum cleaner, its powerful pull capturing or deflecting countless asteroids and comets that might otherwise plunge inward toward the terrestrial planets. This gravitational shield has likely spared Earth from many more extinction-level impacts over the eons, providing a safer stage for life's long, slow drama to unfold. An exoplanet system without such a giant planetary sentinel in its outer reaches could be a far more violent neighborhood, subject to a constant, punishing barrage from space that could reset the clock on evolution again and again. Habitability, therefore, is not just about a world's atmosphere or oceans, it is about the peace of its neighborhood. Now, expand this view to more exotic stellar communities. Imagine a planet not orbiting a single star, but caught in the embrace of 2 or even 3 suns. In such a multi-star system, the simple, circular path of a habitable zone dissolves into a complex, ever-shifting labyrinth of light and shadow. The planet's year would be a dance between different sources of heat and gravity, its surface experiencing wild variations in illumination and temperature as the stars move in their celestial waltz. There could be periods of constant daylight under multiple suns, followed by stretches of deep chill if all stars set simultaneously. Life would need to be extraordinarily resilient, adapting not to a regular cycle of day and night, but to an unpredictable symphony of stellar rhythms, where the very concept of a stable climate is rewritten by orbital mechanics. Finally, consider the power of a planetary embrace itself. We see this in our own solar system, not on a planet, but on Jupiter's moon, Io. Io is kept volcanically molten not by the sun's heat, but by the relentless gravitational kneading it receives from Jupiter and its sister moons. This process, tidal heating, could transform a cold, icy world drifting far from its star. If such a world were locked in a similar gravitational dance with a giant neighbor, the friction generated within its core could melt its interior, driving volcanic activity and potentially creating a subsurface ocean of liquid water insulated beneath a frozen crust. A world we would classify as far outside the traditional habitable zone could, through this planetary puppetry, become a warm, geologically active cradle for life. This reveals the ultimate systemic truth: a planet's potential is a chorus, not a solo. It is composed by the gravity of its moons, the protection or chaos offered by its planetary siblings, and the complex rhythms of its stellar hosts. To find a living world, we must learn to listen to the entire symphony of its celestial system. The longevity of a world's hospitality is perhaps its most fragile quality. Earth's 4 billion-year record of habitability is not a planetary birthright, but a remarkable run of good fortune, a complex balancing act that could have tipped at any point. A planet's ability to support life is a phase in its evolution, a temporary window that opens and may one day close, shaped by the slow, relentless ticking of its internal clock and the aging of its star. Consider a world in its fiery youth. Fresh from its formation, it is a cauldron of radioactive elements and residual heat, its surface a global lava ocean, its atmosphere a thick, toxic haze of outgassed volatiles. For millions of years, it is far too violent for any delicate chemistry to take hold. This is a necessary, sterilizing childhood. Then, as the planet cools, its crust solidifies, and water vapor condenses into the first seas, the window of opportunity cracks open. But this is only the beginning. To keep that window open requires a planetary engine, a source of internal heat from radioactive decay and primordial formation energy. This heat drives the mantle's churn, fueling the volcanism that recycles atmospheric gases, and critically, powers the dynamo that generates a global magnetic field. That magnetic shield is the planet's invisible guardian, deflecting the stellar wind that would otherwise slowly strip away the atmosphere, leaving the surface exposed and barren. Over billions of years, however, that internal heat source inevitably dwindles, the core cools, the geological engine slows and may eventually stop. Without that protective magnetic field, the atmosphere begins a slow, irreversible leak into space. the planet enters its twilight years, growing colder and more desolate, its life-supporting window gently swinging shut. This temporal dimension transforms our search from a snapshot into a search for the right scene in an epic film. We are not just looking for a planet in the habitable zone today. We are looking for one that has been stable within that zone for long enough for life to arise, evolve, and potentially become complex. A world that entered its temperate phase only a few 100 million years ago might be a biological blank slate. Conversely, a world that has been habitable for 6 or 7 billion years, far longer than Earth, presents an awe-inspiring possibility, a biosphere with unimaginable eons to experiment with complexity. The star's own life cycle writes the final act. Our sun is middle-aged, and in another 5 billion years it will swell into a red giant, its outer layers engulfing the inner planets, certainly closing Earth's window for good. For planets orbiting red dwarf stars, the timeline is even more paradoxical. These stars are miserly with their fuel, shining for trillions of years, offering the promise of near-eternal stability. But their early history is one of intense violence, with frequent, powerful flares that could last for the first billion years of a planet's life. Any atmosphere present at formation might be scoured away during this prolonged tempestuous youth. For life to succeed there, it must either arise miraculously after the star finally calms down, or it must find a way to survive that billion-year-long trial by fire, perhaps by originating deep underground and only emerging to the surface once the stellar storms subside. This adds a profound layer of chance to the cosmic lottery. We are not merely searching for a world with the right ingredients, but for one that has mixed them at the right time and for long enough to let something truly extraordinary begin. It means the most Earth-like planet in the galaxy might be one whose story is still in its first chapters, or one that is already nearing its final pages, a fleeting, beautiful moment of balance in the long, dynamic life of a world. Proxima Centauri b is a cosmic riddle sitting right on our cosmic doorstep. This world, with a mass eerily similar to Earth's, orbits the closest star to our own Sun, a faint red dwarf named Proxima Centauri. Its discovery ignited imaginations because it sits within that star's theoretical habitable zone, a tantalizing hint of a temperate neighbor. Yet, everything we have learned since reveals a reality far stranger than any simple Earth twin. This planet is our most powerful case study, a laboratory for every extreme challenge we have discussed, forcing our theories to confront a single, tangible world. Proxima b orbits so close to its dim star that a full year there lasts a mere 11 Earth days. At that intimate distance, the star's gravity has almost certainly captured the planet in a tidal lock. One hemisphere forever faces the perpetual, ruddy glow of Proxima Centauri, while the other is locked in endless, starless night. This creates the ultimate scenario for an eyeball Earth, where the only stable region for liquid water might be a single, narrow band along the twilight line, a ring of potential life encircling a globe of extremes. But the star itself is the greater antagonist. Proxima Centauri is a flare star, prone to sudden, violent eruptions that can blast the planet with X-rays and ultraviolet radiation hundreds of times more intense than what Earth receives from our Sun. These flares are not rare events, they are a fundamental part of the planet's environment. Imagine a world where, without warning, the sky erupts in a searing flash that doubles the star's brightness in minutes, bathing the landscape in a sterilizing glow. The question for Proxima b is not if it has an atmosphere, but whether it could possibly retain one under such a relentless assault. A thick primordial atmosphere might have been stripped away eons ago by this constant stellar fury. Any magnetic field generated by the planet's core would be its first and most vital line of defense, a shield deflecting the charged particles of the stellar wind. Without it, Proxima b could be a barren rock, its surface exposed to the full violence of space. Yet, hope is a resourceful thing. Scientists modeling this harsh world suggest that if an atmosphere did survive, or if it is being replenished by volcanic outgassing, it could be redistributed by powerful global winds flowing from the hot day side to the cold night side. This circulation might just transport enough heat to prevent the entire atmosphere from freezing solid on the dark side, maintaining a fragile planet-wide climate. More intriguing is the possibility of refuge. Even if the surface is a radiation-scorched desert, life, or its precursors, could persist in the profound sanctuary below. Subsurface oceans, insulated by kilometers of rock, could remain liquid due to the planet's internal heat or radioactive decay. Alternatively, in the permanently shadowed craters at the planet's poles, where temperatures might plunge low enough to trap water ice, rare pockets of stability could exist. Proxima Centauri b, therefore, is not a poster child for a second Earth, but a beacon for a new kind of search. It represents the ultimate test of our technology and imagination. Upcoming missions, like advanced space telescopes designed for direct imaging, will attempt to do the extraordinary, capture the faint light reflecting off this world's atmosphere, if it has one. Analyzing that light will give us our first true spectrum of an Earth-mass exoplanet sky, a chemical barcode we can read for signs of water vapor, carbon dioxide, or even the unstable combinations that hint at biology. This closest of worlds embodies the central tension of our quest. Proximity does not guarantee familiarity. The most Earth-sized planet we know may be one of the least Earth-like in its actual conditions, a stark reminder that the universe's most habitable real estate might look nothing like home, and that finding life will require us to look not just for paradise, but for perseverance in the most unexpected places. The TRAPPIST-1 system is a compact cosmic family portrait, a single faint red dwarf star playing host to no fewer than 7 rocky worlds, each one astonishingly close in size to our own Earth. This crowded stellar neighborhood, discovered just a few years ago, instantly became a scientific treasure. It is a ready-made laboratory for comparative planetology, a place where we can study how subtle differences in a planet's recipe birth entirely different worlds, all under the same dim sun. Several of these siblings orbit within or brush the edges of the star's habitable zone, but to call any one of them a straightforward Earth twin would be to miss the system's true chaotic beauty. Their orbits are incredibly tight, with years that last only a handful of Earth days, and they are packed together so closely that from the surface of one world, neighboring planets would appear in the sky not as distant points of light, but as vivid orbs, sometimes larger than our own moon. This intimacy has profound consequences. The planets do not simply orbit their star in isolation. They are in a constant, gentle gravitational tug of war with each other. As they pass by, their mutual pulls stretch and flex their rocky interiors. This friction, known as tidal heating, acts like a hidden furnace within each world. For a planet on the outer, colder edge of the system, this internal heat could be the difference between a frozen, dead rock and a world with a global ocean of liquid water sloshing beneath a thick, icy crust. It could turn what looks like a snowball into a potential water world. Conversely, for a planet orbiting closer to the star, this extra geothermal energy might be too much of a good thing. It could supercharge volcanic activity, turning the surface into a global lava field, or drive such intense geological upheaval that a stable atmosphere could never take hold. The TRAPPIST-1 system presents a stunning paradox, a single stellar environment that could simultaneously host a frozen ocean moon, a temperate rocky world, and a volcanic hellscape, all as siblings. This compact symphony of worlds directly challenges our old habit of searching for a single, perfect Earth-like planet. Instead, it offers a vision of planetary systems as integrated ecosystems, where the fate of one world is written in part by the gravitational whispers of its neighbors. It asks us to consider habitability not as a solitary condition, but as a spectrum of possibilities existing side by side, a whole family of outcomes arising from nearly identical starting materials. Studying this one extraordinary system is like watching nature run the same experiment 7 times with minor variations, giving us front-row seats to the universe's creative process and reminding us that the potential for life might not be a solitary flame in the dark, but part of a broader, interconnected celestial fire. Kepler 452b was announced with a title that sparked global imagination, Earth's older cousin. Here was a world discovered by the Kepler telescope that seemed to check every box on our old wish list. It orbits a star remarkably similar to our Sun, a G-type yellow dwarf, and it sits squarely within that star's temperate habitable zone. Its size, just about 60% larger than Earth's diameter, suggested it was likely a rocky world. For a moment, it felt like the search was over and we had found a mirror. But as astronomers looked closer, they realized this cousin was not a sibling. It was potentially a grandparent, offering a haunting glimpse of a planetary future. The star Kepler 452b calls home is older than our Sun by about 1.5 billion years. It is also slightly brighter. This means for billions of years, this planet has been basking in a slowly intensifying glow. The gentle stellar warmth that might have once nurtured liquid oceans has been steadily, inexorably increasing. This introduces a critical factor we rarely consider: time. A planet's place in the habitable zone is not a permanent address. It is a moving target as its star evolves. For Kepler 452b, the central question becomes one of planetary resilience. Has it managed to adapt to this creeping change, or has it already crossed a threshold from which there is no return? One stark possibility is that Kepler 452b is no longer a blue world but a yellow one. The increasing stellar radiation could have slowly boiled off its oceans, filling the atmosphere with immense amounts of water vapor, a powerful greenhouse gas. This, in turn, would have trapped even more heat, accelerating the evaporation in a vicious cycle known as a runaway greenhouse effect. The planet we hoped was an Earth twin may have transformed, over eons, into a Venus twin, a scorching, arid world shrouded in thick clouds, its surface hot enough to melt metal. Its story would be a cautionary tale of a habitable window that slowly, inevitably closed. Yet there is another path, one that speaks to a planet's ability to regulate itself. Earth maintains its climate over geological timescales through the silicate weathering cycle. Rainfall pulls carbon dioxide from the air, the acidic water reacts with rocks, and the resulting minerals are washed into the ocean, eventually being pulled into the mantle by tectonic activity. The carbon is later released back into the atmosphere through volcanoes, completing a vast planetary thermostat. If Kepler 452b possesses a similar active geology and water cycle, it might have been able to counter the increasing solar heat by slowly drawing down carbon dioxide levels, maintaining a stable climate even as its sun grew brighter. In this scenario, it could be a mature, stable world, its biosphere having had far longer than Earth's to evolve and complexify, a true elder statesman of a planet. But the uncertainties do not end with its climate. That 60% larger size is a lingering puzzle. It places Kepler 452b in a troubling gap between a rocky super-Earth and a gaseous mini-Neptune. With our current technology, we cannot yet measure its density to know for sure if it is solid or puffy. It could be a massive, water-rich world with a global ocean and a thick, steamy atmosphere, or it could have a small rocky core enveloped by a vast hydrogen-helium envelope, making it utterly uninhabitable by any Earth-like standard. This single world, perhaps the most promising analog we have found, embodies the entire journey of this new science. It looks familiar from a distance, a rocky planet around a sun-like star in the right place. Yet the closer we look, the more its unique story unfolds, a narrative written in the slow aging of its star, the potential resilience of its geology, and the ambiguous nature of its construction. Kepler 452b teaches us that the most Earth-like candidates are not answers but deeper, more intricate questions. They are portals into understanding how planets live, age, and sometimes perish over cosmic timescales far beyond our own. This search for life, then, is a search for a ghost in the machine, a signal hidden within the noise of an alien atmosphere. We call these potential signals biosignatures, and our entire strategy has been built around the chemistry of our own living world. The simultaneous presence of oxygen and methane in Earth's air is a chemical paradox. These gases react with each other, so finding them together means something, likely biology, is constantly replenishing them. It is a compelling fingerprint, one we are desperately trying to find in the light of other stars. But this approach carries a profound and hidden risk, the risk of planetary bias. We are looking for life as we know it, and in a universe of Hycean planets, lava worlds, and puffy giants, that might be the surest way to miss it entirely. Consider a Hycean world with its deep, warm ocean beneath a hydrogen sky. Life in that sunless abyss would not rely on photosynthesis. It would not split water molecules to produce oxygen as a waste product. Its metabolism would be based on chemical reactions we can scarcely predict, perhaps producing gases like dimethyl sulfide or phosphine as byproducts, compounds that would be startlingly out of place in that environment. On a volcanic world, biology might be intimately tied to the sulfur and iron spewing from vents, leaving its signature not in the atmosphere at all, but in strange mineral formations or isotopic ratios in the surrounding rock, clues we could only detect by landing on the surface. And in the thick hydrogen atmosphere of a mini Neptune, any floating, aerial life would likely produce metabolic gases that are lightweight, like certain hydrocarbons, which would rise and mix in that vast aerial ocean, creating a subtle chemical gradient we must learn to recognize. The dilemma is stark. By training our most powerful future telescopes to look primarily for the oxygen-methane combination, we might be tuning our instruments to hear only one note in a cosmic symphony. A truly alien biosphere, thriving under alien rules, could be broadcasting its existence on a completely different frequency, one we are not even listening for. This forces a fundamental expansion of the search protocol. Scientists are now compiling what they call agnostic biosignatures, a broader suite of chemical combinations that are difficult to explain without biology, regardless of the specific biochemistry involved. This list includes gases like nitrous oxide, methyl chloride, and even the artificial chlorofluorocarbons that, if found, would point not just to life but to technology. This brings us to the ultimate signature, the technosignature. While biosignatures hint at microbes or algae, technosignatures would be the markers of a civilization advanced enough to alter its planet on a scale we could detect from light years away. This could be the persistent glow of city lights on the planet's night side, the sudden appearance of artificial compounds like those CFCs in the atmosphere, or even the faint, structured radio signals we have listened for decades. The search for technosignatures acknowledges a breathtaking possibility that the greatest discovery in human history might not be a microbe but a message, or the silent, luminous evidence of another mind building its own world. Ultimately, this shift in thinking transforms the goal. We are no longer just hunting for a pale blue dot. We are learning to read a much richer and more varied library of planetary stories. Each world, from the tidally heated moon to the hydrogen-shrouded ocean planet, has its own language of chemistry and light. Our task is to become fluent in these alien dialects, to recognize the fingerprint of life not as a single, familiar shape, but as any pattern of beautiful, persistent complexity that defies the sterile laws of equilibrium. The universe may not announce life with a flash of green or a breath of oxygen, but with a subtle chemical whisper that says, something here is fighting against the silence. The ghostly fingerprints of alien atmospheres are about to come into startling focus. For all our theorizing about super-Earths and Hycean worlds, we have been like astronomers from centuries past, sketching the geography of distant continents based solely on the silhouettes of ships passing in the fog. Our knowledge is profound, yet profoundly indirect, built on the wobble of a star or the faint dimming of its light. That era of inference is ending. A new generation of telescopes, both in space and on remote mountaintops, is poised to open a direct window onto these alien skies, transforming our pixelated guesses into high-definition portraits. The James Webb Space Telescope, already rewriting cosmic rules, is just the opening act. Its powerful infrared eyes are uniquely suited to dissect the light filtering through exoplanet atmospheres, searching for the molecular signatures of water vapor, carbon dioxide, and methane. But Webb is a pathfinder. The true revolution will come from its successors, instruments designed with one explicit goal: to find and study another Earth, or whatever astonishing form that Earth might take. On the high deserts of Chile, the extremely large telescope is rising from the rock. With a primary mirror nearly the size of a blue whale is long, this ground-based behemoth will use advanced adaptive optics to cancel out the twinkling blur of our own atmosphere. Its goal is audacious: to directly capture the faint, reflected glow of a rocky planet orbiting a nearby star, separating its pinpoint of light from the overwhelming glare of its sun. This is the leap from detection to direct imaging, from knowing a planet is there to actually seeing it as a distinct colored dot in the void. That dot, however, will hold a universe of information. By analyzing its light with a technique called spectroscopy, astronomers will be able to read the chemical barcode of its atmosphere. Different gases absorb specific colors of starlight, creating dark lines in the spectrum that act as a unique identifier. We will not just know if an atmosphere exists, we will know its composition, its pressure, and whether it contains clouds or high-altitude hazes. We could witness the seasonal ebb and flow of carbon dioxide on a distant world, or map the global temperature differences between the day and night sides of a tidally locked planet, watching our climate models succeed or fail in real time. This data will be the crucible that tests our wildest hypotheses. Is that super-Earth shrouded in a steamy water vapor atmosphere, or is it a mini Neptune with a puffy hydrogen envelope? Does the Hycean world candidate show the spectral signature of water vapor and methane in a hydrogen-rich sky, hinting at its hidden ocean? The speculations of the last decade will face the uncompromising verdict of observation. The ultimate dream, however, lies a bit further in the future. Concepts like the proposed Habitable Worlds Observatory envision a space telescope specifically designed to image dozens of Earth-like planets around Sun-like stars. It would use a sophisticated starlight blocking system, a coronagraph, to create an artificial eclipse, allowing the faint planetary light to shine through. This instrument would not just take a single snapshot. It could monitor these worlds over time, mapping their weather patterns, watching for the changes that might indicate continents and oceans, and searching for the subtle, unstable chemical combinations that shout biology. The search will evolve from finding planets in the habitable zone to meticulously characterizing their actual habitability. We will move from asking if a world could have liquid water to measuring the chemical gradients in its air that suggest something is actively consuming and producing gases. The first biosignature detection will not be a simple yes or no, but a years-long process of validation, ruling out every possible geological explanation for that tantalizing spectral line until only one extraordinary possibility remains. This imminent leap in vision promises something more profound than discovery. It promises context. we will no longer study these worlds as isolated curiosities, but as a comparative collection, a galactic gallery of planetary outcomes. By seeing so many different atmospheres under so many different stars, we will finally understand which factors are common and which are rare, which paths lead to stable climates and which lead to sterile wastelands. The data flowing from these new eyes on the cosmos will tell the true story of planets, not as we imagine them to be, but as they actually are, in all their bewildering and beautiful variety. This cumulative journey reveals a truth more profound than any single discovery. We are witnessing a fundamental paradigm shift in our understanding of the cosmos. The term Earth-like can no longer serve as a checklist for a duplicate of our world, a specific blueprint of oceans, continents, and a nitrogen sky. That definition is too narrow, too parochial for a universe that clearly operates on a grander, more imaginative scale. The category must evolve, expanding into something far more powerful and inclusive, potentially habitable or perhaps life-capable. This new definition is not a single destination, but a vast spectrum of possibilities. It encompasses the crushing atmospheres of super-Earths, the sunless abysses of icy ocean moons, the permanent twilight bands of eyeball planets, and even the temperate cloud decks of puffy mini-Neptunes. What unites these wildly different worlds is not a specific recipe of rock, water, and air, but a deeper, more fundamental potential, the ability to maintain an environment where liquid can exist, where energy can flow, and where complex chemistry can persist, interact, and perhaps over deep time evolve. This shift is both deeply humbling and utterly exhilarating. It humbles by placing our own planetary home in its proper context, not as a universal standard, but as one single, beautiful day to point in a sprawling gallery of planetary art. Yet it exhilarates by suggesting that life, if it exists out there, is likely to be far more diverse, more resilient, and more ingenious than we ever dared to dream. It implies that biology is not a fragile flame, requiring the exact shelter of an Earth-like hearth, but a persistent spark, capable of catching hold in the most astonishing and unexpected corners of reality. The search is no longer for a mirror, but for a reflection of a deeper principle, the signature of complexity itself written in alien chemistry and under alien skies. This dizzying array of possibilities forces a deeply personal question upon us. With so many paths a world can take, where does our own pale blue dot fit in? For generations, we have assumed Earth represented the cosmic norm, the default setting for a living planet. But what if, in the grand scheme of the galaxy, we are the exotic ones? Our Sun is a stable, yellow dwarf, a stellar type that makes up less than 10% of the stars in the Milky Way. We have a giant moon, proportionally larger than any other moon orbiting a rocky planet in our solar system, acting as a steadying hand on our climate. Our geology features the constant, gentle recycling of plate tectonics, and our atmosphere is a precise, breathable blend of nitrogen and oxygen. Each of these factors on its own might not be unique. But the combination, the specific recipe that led to a global, temperate climate stable for billions of years, could be extraordinarily rare. Perhaps the universe's most common habitable real estate is not a world of varied continents and deep blue oceans, but a tidally locked eyeball planet around a faint red dwarf, or a global water world with no land in sight. In these more common environments, life might flourish in simpler, more resilient forms, microbial or aquatic, perfectly adapted to permanent twilight or a sunless ocean abyss. The leap from that existence to a civilization that builds telescopes, writes poetry, and wonders about its place in the cosmos might require a very specific and unusually tranquil planetary cradle. This idea is sometimes called the cosmic zoo hypothesis. It suggests that while life itself may be a relatively common phenomenon in the galaxy, the conditions that nurture intelligent, technological species like us could be a fluke, a rare convergence of geological and astronomical luck. We might not be hearing from other civilizations not because they do not exist, but because they almost never reach a point where they can look outward and communicate. Their worlds, while teeming with biology, might never provide the stable platform, the accessible resources, or the evolutionary pressures that lead to technological curiosity. This perspective is not a lonely one, but a deeply illuminating shift in focus. It asks us to value life in all its potential forms, not just the kind that mirrors our own journey. It means the greatest biological show in the galaxy might be playing out in the deep oceans of icy moons, in the thick clouds of puffy planets, or in the chemical soups around hydrothermal vents on volcanic worlds. We are challenged to expand our empathy beyond the human experience, to imagine sentience born in a perpetual liquid medium, or intelligence that measures time in the slow growth of continents that do not exist. Our search, then, becomes a dual mission. We are looking for both the familiar and the profoundly alien, for cousins who share our story, and for life forms whose very existence will rewrite our understanding of biology. This humbling possibility does not diminish our world, it makes its delicate, intricate balance all the more precious. We are forced to see Earth not as a template, but as a single, beautiful, and perhaps improbable verse in an epic cosmic poem. This search for the truly unknown demands a new kind of toolkit. Our current missions to other worlds, like the rovers on Mars or the planned probes to the icy moons, are engineering marvels, but they are built on a very Earth-centric logic. They are designed to sniff out the chemical signatures of life as we know it, searching for organic molecules, amino acids, and the specific isotopic ratios that, on our planet, signal biological activity. Yet the expanding gallery of possible habitable worlds reveals a critical flaw in this approach. What if the life we find does not use DNA at all, or thrives in a solvent like liquid methane where our familiar biochemistry would simply freeze? The next generation of astrobiology must become more imaginative, designing experiments that do not look for a specific guest, but for the universal party happening in the house. This means shifting focus from hunting for particular molecules to detecting the hallmarks of any living system, what scientists call agnostic biosignatures. These are the universal traces of complexity. Life, in any form, must harvest energy from its environment, whether from sunlight, chemical gradients, or thermal heat. It must create order from chaos, building complex structures and maintaining a state that defies the natural drift toward equilibrium. And it must process information, adapting and responding to its surroundings. An instrument that can detect an unexpected chemical gradient in the soil of Mars, or measure an inexplicable flux of energy in the plumes of Enceladus, could be the key. It would not tell us what the life is, only that something here is actively working against the stillness. The ocean moons in our own solar system are becoming the perfect training grounds for this new philosophy. Europa, orbiting Jupiter, and Enceladus, circling Saturn, are both believed to harbor vast, global saltwater oceans beneath their icy shells. Enceladus, in particular, shoots geysers of that subsurface material directly into space, offering a free sample for a passing spacecraft to analyze. A future mission flying through those plumes will not just be looking for Earth-like cells, it will be conducting a broad chemical census. It will search for patterns of molecular complexity that are statistically unlikely to form through geology alone, for an imbalance of gases that suggests constant replenishment, or for structures with a handedness, a preference for left or right-handed versions of molecules, which on Earth is a strong indicator of biological processes. These are the kinds of tests we must perfect close to home, because they are the very same tools we would need to understand the atmosphere of a Hycean world light years away, or to interpret the chemistry of a tidal heated lava planet. The goal is to build explorers that are not pre-programmed with a single answer, but equipped with the curiosity to recognize a question written in an alien language. We are preparing our machines and our minds for the moment they might brush against a form of biology that shares no common ancestor with us, a life built from a different set of instructions entirely. Our search for another Earth ultimately becomes a search for ourselves, a quest to understand what home truly means. The revelation that the habitable zone is filled with worlds of unimaginable variety forces a quiet philosophical revolution. If a living planet can be a global lava field, a hydrogen-shrouded ocean, or a perpetual twilight band, then Earth is not the model for the universe. It is one exquisite possibility among countless others, a single brushstroke in an endless cosmic painting. This realization carries a dual weight, a poignant sense of cosmic solitude paired with an overwhelming awe at the universe's boundless creativity. We are alone in the sense that our specific combination of blue oceans, green forests, and breathable air may be extraordinarily rare, a local masterpiece. Yet we are profoundly connected by the underlying physics and chemistry that seem to build planets and perhaps spark life everywhere, following universal rules to generate infinite diversity. The same processes that sculpted our mountains and filled our seas likely operate on worlds 1,000 light-years away, but they are mixed in different proportions under different suns, yielding results that stretch our very definition of a world. This transforms our view of Earth from a universal standard into a singular, precious expression. The rustling of leaves in a forest, the crash of a wave on a shore, the vast sweep of a desert under a clear sky, these are not cosmic norms. They are the beautiful, specific outcomes of our planet's unique history, a history that could have unfolded in a million other ways. This awareness deepens our environmental responsibility. It highlights the fragility of this particular miraculous experiment. There is no backup Earth because another world exactly like this one almost certainly does not exist. Our stewardship becomes about preserving a unique work of cosmic art. At the same time, it expands our sense of kinship. If life does exist on a Hycean world or in the clouds of a mini Neptune, it would be our distant relative in the grand story of the universe, a cousin born from the same fundamental principles of matter and energy, yet shaped by an utterly alien environment. This perspective does not diminish our world, it elevates it. We are invited to see Earth with new eyes, not as a commonplace rock, but as a rare and vibrant gem in the cosmic dark, while simultaneously opening our hearts to the possibility of other gems, of other forms of beauty and consciousness, flourishing under alien suns in ways we are only beginning to dream. The search for these strange new worlds is not confined to university labs or mountaintop observatories. It is a story being written by thousands of hands across the globe, a testament to the power of collective curiosity. Many of the exoplanets we have discussed, those puzzling worlds in the habitable zone, were first flagged not by a supercomputer, but by a person sitting at their kitchen table. This is the quiet revolution of citizen science, where the public becomes an essential partner in unraveling cosmic mysteries. Projects like Planet Hunters invite volunteers to look at the same data collected by telescopes like Kepler and TESS, the precise measurements of starlight that hold the secrets of distant solar systems. The task is deceptively simple: to scan graphs for the tiny, periodic dips that occur when a planet passes in front of its star. While algorithms are incredibly fast, they can be programmed to look for specific, expected patterns. The human brain, however, excels at spotting the odd, the unusual, the outlier. A volunteer might notice a slight irregularity in the data, a double dip, or a strange shape that a computer program filtered out as noise. That anomaly, highlighted by a curious human eye, can lead astronomers to re-examine the data and confirm the existence of a planet with an eccentric orbit, or even a world orbiting in a binary star system, scenarios that challenge our standard models. This public engagement does more than just process data. It builds a global community with a direct stake in discovery. When a new planet is validated, the names of the citizen scientists who helped find it are often included in the published research. A teacher in Brazil, a retiree in Japan, or a student in Norway can share in the thrill of knowing they contributed to expanding the map of our galaxy. It democratizes the profound act of discovery, making it clear that you do not need a doctorate to help answer one of humanity's oldest questions. The next world that shatters our definition of Earth, like a bizarre Hycean planet or a super-Earth with impossible geology, might very well be first spotted by an artist with a knack for patterns or an enthusiast during their evening scroll. This collaborative spirit reminds us that the quest to understand our place in the cosmos is not a solitary academic pursuit, but a shared human endeavor woven together from the curiosity of people everywhere. This profound silence echoes a question first posed decades ago. If the universe is so vast and ancient, with countless stars and potentially trillions of planets, why have we heard nothing and seen no one? This is the heart of the Fermi paradox. The discovery of these strange, challenging habitable zones might offer a new and somewhat somber perspective on that cosmic quiet. It introduces the idea of a great filter, a hypothetical barrier so difficult to overcome that it prevents life from progressing to the point of building civilizations and filling the galaxy. Perhaps the universe is teeming with simple, microbial life in those deep oceans and thick atmospheres, but the leap from a single-celled organism to a complex, intelligent, spacefaring species might require a planetary cradle of astonishing stability and specific resources, a combination far rarer than liquid water alone. Our own Earth, with its stable axial tilt, protective magnetic field, calm star, and accessible surface minerals, might represent an exceptional sanctuary. For every world like ours, there could be 1,000 others where life gets stuck. Imagine an intelligent species evolving in the global ocean of a Hycean world. They might develop profound culture and philosophy in their sunless abyss, but without fire, without metals, without the ability to ever see the stars, the leap to astronomy and spaceflight could be physically impossible. Their world is habitable, even inhabited, but it is also a beautiful, inescapable cage. Or consider a civilization on a tidally locked eyeball planet, confined to a single narrow band of twilight. With resources limited to that one temperate ring, and with hurricane-force winds as a permanent feature of their environment, could they ever develop the sustained, global cooperation needed for advanced technology? Their struggle might be against planetary geography itself. The filter could be behind us, meaning we are the miraculously lucky ones who have already passed through a series of cosmic bottlenecks. Or the more unsettling possibility is that the filter lies ahead. Perhaps the technological adolescence of a civilization, the point where it gains the power to alter its planet or destroy itself, is the stage most species fail to navigate. The very intelligence and tool building that allowed us to peer into the cosmos could contain the seeds of our own undoing. These bizarre habitable worlds show us the countless ways a planet can be life-friendly, yet still be a developmental dead end for intelligence. They frame our solitude not necessarily as a sign that life is rare, but that certain kinds of life, the kind that looks back at the universe and wonders, might be the universe's most fragile and improbable creation. The true weather on these worlds remains a mystery, a forecast written in a language we are still learning to read. To translate it, scientists have built entire planets inside supercomputers, digital laboratories where they can test the physics of alien skies. These are climate models of astonishing complexity, not predicting next week's rain, but simulating the global atmospheric flow of a world 1,000 light-years away. The process begins with a set of assumptions, the raw ingredients of a planet. Astronomers feed in the known variables, the precise amount of energy pouring from the star, the planet's orbital distance, its likely rotation rate, and its estimated size and mass. Then comes the artful speculation, the proposed atmospheric recipe, a thick blanket of carbon dioxide, a hydrogen-rich shroud, or a steamy mix of water vapor. With these inputs, the virtual world is born, and the simulation begins to run, calculating how heat is absorbed, reflected, and transported across the globe over thousands of virtual years. For a tidally locked eyeball planet, the model might reveal a permanent planet-spanning storm. The immense temperature difference between the scorching day side and the frigid night side doesn't just create a breeze, it fuels a relentless hurricane-force wind roaring from the hot hemisphere to the cold one. This atmospheric river would constantly scour the narrow temperate band, a never-ending tempest that any potential life would have to endure. Conversely, for a super-Earth with a crushing atmosphere, the model shows how that dense air acts as a global conveyor belt. The incredible pressure and heat-trapping capacity can smooth out temperature extremes, creating a world with surprisingly uniform warmth from pole to pole, but with surface conditions that would liquefy metal and crush any submarine we could build. These digital experiments often yield surprises that challenge our intuition. One simulation might show that a water-rich world with a certain atmospheric composition could, counterintuitively, plunge into a global snowball state, its oceans freezing solid despite orbiting squarely in the habitable zone. Another might reveal a self-stabilizing feedback loop on a volcanic world, where increased heat triggers more cloud formation that then reflects sunlight, cooling the planet back down, a natural planetary thermostat we never anticipated. This virtual exploration is more than just scientific play, it is essential preparation. These models create a library of possible climatic outcomes, a set of predictions against which we can compare our future observations. When the next generation of telescopes finally captures the faint light from an exoplanet's atmosphere, the data will be a chaotic jumble of spectral lines. To make sense of it, to understand if that jumble represents a stable ocean world or a runaway greenhouse, we will turn to these simulations. They provide the context, telling us what the signature of a global hurricane looks like in infrared, or how the heat glow from a lava planet differs from that of a temperate rocky one. They are the guidebooks for a journey we have not yet taken, mapping the weather of worlds we can only, for now, dream of visiting. Our gaze has been fixed on planets, but we may have been overlooking their most promising companions. The search for life is expanding into a new frontier, the hunt for exomoons, worlds orbiting other worlds. Imagine a gas giant, a Jupiter-like planet, drifting gracefully through the temperate band of its star's habitable zone. This giant world itself is not a candidate for life as we know it, a swirling ball of hydrogen with no solid surface, but circling it, held in its powerful gravitational embrace, could be a rocky moon, a world with its own story to tell. This scenario creates a habitable zone within a habitable zone, a nested possibility that adds yet another layer of wonder to our cosmic search. Just as Jupiter's moon Europa is believed to harbor a vast, global ocean beneath its icy crust, an exomoon orbiting a giant in the stellar sweet spot could be a water-rich sanctuary. Its surface might be a frozen, cratered landscape, but deep below, insulated by kilometers of ice, a liquid ocean could slosh against a rocky seafloor, warmed not by the distant sun, but by the moon's own internal fire. This heat comes from a relentless gravitational tug-of-war. As the moon orbits its giant planet, the planet's immense gravity stretches and squeezes the moon's rocky interior. This friction, known as tidal heating, acts like a geothermal furnace buried at the moon's core. It is this energy that could keep a subsurface ocean liquid for billions of years, completely independent of the amount of starlight the moon receives. An exomoon sky would be a spectacle of complex illumination. The primary light would come from the distant star, of course, casting a faint, sun-like glow. But for much of the moon's day or night, the giant planet would hang in the sky, a colossal, striped marble reflecting a significant amount of that starlight back down onto the moon's surface. This planetary shine would provide a secondary source of warmth and light, potentially softening the darkness of a long night or adding extra energy to the dayside. This dynamic creates a climate scenario that could be more stable than that of a tidally locked planet. A moon's rotation on its own axis is separate from its orbit around its planet. This means it could have a regular day-night cycle relative to the star, even as it circles the giant world. It would not be condemned to one permanent day side and one eternal night side. Instead, it might experience normal days with the added wonder of watching its host planet go through phases, from a thin crescent to a full, glorious disk that dominates the heavens. This rotational freedom could help distribute heat more evenly, preventing the extreme temperature contrasts that plague eyeball planets. The potential for such worlds is staggering, but finding them is a monumental technical challenge. Detecting an exoplanet is difficult enough, like spotting a firefly next to a spotlight from thousands of miles away. Detecting an exomoon is like trying to see that firefly's even tinier companion clinging to its side. Current methods involve looking for subtle wobbles in a planet's transit signal, or minute variations in the timing of its orbits, hints that something with its own gravity is tugging on the planet. While no confirmed exomoon has been found yet, astronomers are actively developing the tools and techniques for this next great hunt. The existence of exomoons would revolutionize our catalog of habitable real estate. It suggests that life could flourish not on the primary planets we have been fixated on, but on their satellites, hidden gems warmed from within. It challenges us to broaden our search parameters once more, to listen for the whispers of life not just from stars and their planets, but from the intricate gravitational dances within a planetary system itself. A planet's current address in the habitable zone is merely a single frame in a billion-year film. To understand its true character, we must rewind the cosmic tape and watch its entire story unfold from birth. Every world we see is a traveler on an evolutionary journey, and its present condition is just one stop along a path that could lead to paradise or desolation. Consider the classic tale of a rocky planet's adolescence. It begins in fire, a churning sphere of magma after its violent formation. For millions of years, it is a global lava ball, its surface an incandescent sea. But as it cools, its interior begins to exhale. Volcanoes spew forth a primordial atmosphere rich in water vapor, carbon dioxide, and nitrogen. This thick, steamy shroud acts as an insulating blanket, trapping the young star's heat. Then, as temperatures drop further, a miraculous phase change occurs. The water vapor condenses, and the first rains begin to fall, a downpour that lasts for millennia, filling the low basins to create the planet's first global ocean. For a time, this world is a water world, a blue marble with perhaps only scattered volcanic islands breaking its endless sea. This is a potentially habitable stage, a cradle waiting for chemistry to stir. But the story does not end there. The aging of the star introduces a slow, relentless pressure. Most stars, like our own sun, grow gradually brighter over billions of years. The gentle warmth that once nurtured a global ocean slowly intensifies. On a world with a robust geological carbon cycle like Earth's, this can be managed. Rainfall pulls carbon dioxide from the air, locking it in rocks, which prevents a runaway greenhouse effect. But if that planetary thermostat breaks, if volcanism ceases and the carbon cycle stalls, the increasing solar heat triggers a catastrophe. The oceans begin to warm and more water evaporates into the atmosphere. Water vapor is itself a potent greenhouse gas, trapping even more heat in a vicious, self-reinforcing cycle. The oceans could reach a tipping point where they begin to boil in earnest. The water molecules, broken apart by sunlight in the upper atmosphere, allow lightweight hydrogen to escape into space forever. Over eons, the planet bleeds its water away. The global ocean shrinks, salt flats expand, and the once blue world slowly transforms into a dry, scorching desert. Its atmosphere now thick with the leftover carbon dioxide, a permanent monument to its lost seas. This is not speculation, it is the suspected fate of Venus, a world that may have once been a twin to Earth. Conversely, a planet might begin its life in deep freeze, an ice ball locked outside the traditional habitable zone. A cataclysmic event can rewrite its destiny. A massive asteroid impact or a prolonged period of intense volcanic activity driven by a radioactive core can pump enough greenhouse gases into its thin atmosphere to trigger a rapid thaw. The ice melts, revealing a rocky surface and creating liquid water oceans. This world suddenly, dramatically, enters a habitable phase, a late bloomer in the planetary garden. This deep time perspective solves a critical puzzle. Two planets can occupy the same orbital band today, basking in identical amounts of starlight. Yet one could be a vibrant ocean world and the other a barren wasteland. Their identical addresses tell us nothing of their personal histories. One might be a young water world still in its prime, the other a senescent desert that has already lived and lost its golden age. Their surface conditions are not just products of their location, but of the specific sequence of geological and atmospheric events that shaped them over billions of years. A planet's habitability is not a permanent state, but a chapter, and to find a world where that chapter is open right now, we must learn to read not just its current climate, but the entire book of its life. The classic habitable zone diagram is a map drawn for one specific traveler. It charts the orbital distances where a planet like ours with water-based life could exist. Yet this map assumes every explorer in the cosmos is following the same guidebook, needing the same conditions. What if the universe is filled with travelers reading entirely different maps? Our definition hinges on liquid water as the universal solvent for carbon-based biology. But this is a profound assumption, one that may blind us to the vast majority of biological real estate. To truly map where life could be, we must redraw our charts for every possible biochemistry. For a form of life built not on carbon in water, but on silicon in liquid methane, the entire concept of the habitable zone shifts into the deep freeze. Methane remains liquid at temperatures far below the freezing point of water. A world that orbits far from its star, in the chilly realm of the ice giants, could have rivers and lakes of liquid methane on its surface. For such a biology, our cozy, temperate zone would be a scorching desert, while the frozen outskirts of a solar system become the prime neighborhood. The habitable zone is not a fixed ring, it is a spectrum that changes with the chemistry of life itself. Then there are the worlds that make their own warmth, rendering the stellar habitable zone almost irrelevant. Consider an icy moon or a rogue planet untethered from any star drifting through the interstellar dark. On the surface, it is a frozen wasteland, but deep within, heat from radioactive decay in its core or from the relentless gravitational kneading of a nearby giant planet can maintain a vast global ocean beneath the ice. For life in that sunless abyss, the concept of orbiting in a star's Goldilocks band is meaningless. The only requirement is that the world is massive enough to generate and retain that internal heat and to hold onto its water. Its habitable zone is not a place around a star, but a condition within itself, a hidden, warm heart beating in the cosmic cold. Even the skies of gas giants, which we dismiss as uninhabitable, could host their own unique zones. A life form adapted to float in the dense atmosphere of a Jupiter-like planet would not care about a solid surface or liquid water seas. Its habitat would be a specific layer within those swirling clouds, a band where the pressure and temperature are just right for its complex chemistry to operate, perhaps using ammonia or hydrocarbons as a solvent. This aerial biosphere would exist in a permanent, stable stratum, a sky habitat defined by atmospheric physics, not orbital distance. This perspective transforms a simple diagram into a complex, multi-layered atlas. A single planetary system could contain several overlapping habitable zones for different kinds of life. The traditional water-based zone might host an Earth-like planet. Further out in the methane zone, a Titan-like moon could harbor its own cryogenic biology. And in the atmosphere of a giant planet orbiting between them, a persistent cloud deck might cradle floating organisms. We are no longer looking for a single bullseye, but for an entire target filled with concentric rings, each representing a different set of rules for existence. It suggests that life, in its boundless potential, is not confined to the narrow band we once prescribed. It could be almost anywhere, waiting in the cold, the dark, or the clouds, following a map we are only beginning to sketch. The dream of reaching another world forces a practical choice among these cosmic wonders. If humanity ever builds a starship, which of these bizarre planets would earn our first visit? Proxima Centauri b holds the powerful allure of proximity, a mere 4 light-years away. Yet its likely tidal lock and the violent flares from its red dwarf star present a formidable gauntlet. Any landing party would face a world of permanent extremes, where one hemisphere is bathed in potentially sterilizing radiation while the other is locked in deep freeze. The scientific prize of studying a nearby Earth mass world is immense, but the price of survival there could be living permanently underground, shielded by rock from the stellar fury above. A Hycean world, with its promise of a warm, global ocean, calls to our spirit of oceanic exploration. Imagine submersibles descending into an alien abyss that has never known sunlight, probing depths that could hide entire ecosystems built on chemical energy. Yet this world offers no shore, no solid ground, no place to build anything but floating or submerged habitats. It is a destination solely for discovery, not for settlement. The immense gravity of a super-Earth presents a more fundamental obstacle: the energy required to land safely on a world where you weigh 2 or 3 times your Earth weight, and then to launch back into space against that crushing pull, might make any mission a one-way trip. The very forces that make such a world fascinating, its dense atmosphere and profound geology, also make it a potential planetary prison for human explorers. A tidally locked eyeball planet offers a unique laboratory, a single global line of temperate terrain bordered by 2 sterile deserts. Scientists could study an entire biosphere compressed into one narrow band, but they would do so in the teeth of permanent hurricane-force winds generated by the extreme temperature divide. The choice of target ultimately reveals our purpose. Is the goal to find any life, however strange? Then the hidden ocean of a Hycean world or an icy moon might be best. Is it to seek a new home for humanity? Then none of these options seem welcoming, each presenting a different form of exile. This thought experiment strips away the romance of discovery and confronts us with engineering and biology. It reveals that a planet can be habitable in the cosmic sense, capable of supporting some form of life, while remaining utterly inhospitable to us. Our species evolved within a very specific set of planetary conditions: a gentle gravity, a stable climate, a protective magnetic field, and a calm star. The strange worlds of the habitable zone show us that this combination is not a universal standard, but a very specific and perhaps very rare recipe. They teach us that the most profound discovery might not be a new Earth, but the final, humbling realization of how perfectly and how precariously our own world is tailored to our existence. A planet's climate is not written by its star alone, but also by the dust in its air and the jewels in its sky. We often picture alien worlds as solitary spheres, but many could be adorned with vast, intricate rings or perpetually shrouded in high-altitude hazes. These are not mere decorations, they are active climate engineers capable of rewriting a world's temperature and seasons with silent, celestial influence. Consider the dramatic shadow of a ring system like Saturn's. From the surface of a ringed planet within a habitable zone, these bands of ice and rock would cast a profound, moving darkness across the landscape. This isn't a brief eclipse, but a permanent, latitudinal stripe of shade that changes with the planet's orbit. The ring shadow could block a significant percentage of incoming stellar radiation, cooling entire bands of the planet year-round. This creates a world with wildly complex microclimates. The equator, permanently in shadow, might be a cold, dry belt, while the mid-latitudes, which dip in and out of full sunlight, could experience the most temperate conditions. The poles, bathing in continuous light for half the year, might paradoxically become the warmest regions. Seasons on such a world would be a bizarre dance of light and shadow, not just temperature, forcing any potential life to adapt to a rhythm utterly foreign to our own. Beyond these grand orbital architectures, a planet's own atmosphere can hold a persistent veil. Global dust storms, perhaps driven by powerful winds from vast deserts, could loft fine particles high into the stratosphere, where they linger for years, reflecting sunlight back into space. On a world already receiving minimal warmth from a faint star, such a planetary sunshade could tip the balance, plunging the entire globe into a permanent ice age. Conversely, that same dust could act as an insulating blanket if it consists of darker, carbon-rich particles that absorb heat. The source of this dust is a story in itself. It might not be from deserts at all, but from relentless volcanic eruptions, constantly pumping ash and sulfur aerosols into the sky, creating a permanent, cooling haze that lowers global temperatures. Or, in a remarkable interaction with the galaxy itself, a planet drifting through a dense molecular cloud could be steadily dusted with fine interstellar particles, a gentle cosmic snowfall that subtly alters its atmospheric chemistry and its ability to retain heat. These factors represent the fine print in a planet's climate contract. Two worlds, identical in orbit, size, and atmospheric composition, could have radically different fates based on the presence or absence of a ring system, or the frequency of planet-spanning dust storms. A world on the cooler edge of the habitable zone might avoid a global snowball state solely because a thin, high-altitude haze perfectly balances the amount of sunlight it reflects and absorbs. Another, closer to its star, might be saved from a runaway greenhouse by the periodic cooling effect of massive volcanic eruptions. This adds a stunning layer of chance to planetary evolution. It suggests that the long-term stability of a climate, that precious window for life, can hinge on geological accidents and celestial accessories we are only beginning to appreciate. When we model these alien environments, we must now account for the dust in the machine, the rings in the sky, understanding that a world's true habitability is sculpted by both its grandest features and its most delicate floating details. But a planet's fate is not decided by its star alone. We must zoom out further, to a scale so vast it encompasses the entire swirling architecture of a galaxy. Some astronomers propose that within this grand design, there exists yet another layer of cosmic real estate, a galactic habitable zone. This is not a ring around a single sun, but a broad, sweeping region within a galaxy where the conditions are just right for complex life to emerge and persist. It is the idea that our address in the Milky Way itself might be part of a rare, fortunate neighborhood. Venture too close to the bustling, brilliant core of a galaxy like our own, and you enter a realm of extreme peril. Here, stars are packed together in a dense stellar metropolis. The sheer gravitational traffic increases the risk of a nearby star passing too close, disrupting the delicate orbits of planets in their systems. More critically, the rate of catastrophic stellar explosions, supernova, would be far more frequent. a nearby supernova would bathe any orbiting planets in a flood of lethal radiation, potentially sterilizing entire systems and resetting the evolutionary clock again and again. It is a dazzling but deadly urban center of the cosmos. On the other hand, drift too far out into the galactic hinterlands, the sparse, dark outskirts of the spiral arms. Here, the danger is not violence but poverty. In these remote regions, the concentration of heavier elements, what astronomers call metals, is much lower. These elements, forged in the hearts of earlier generations of stars and scattered by their explosive deaths, are the essential building blocks for rocky planets like Earth. A star system born in this elemental desert might form gas giants, but lack the raw materials to construct solid, terrestrial worlds with rich geologies and the chemistry necessary for life as we know it. Our own solar system seems to occupy a galactic Goldilocks zone. We orbit in a relatively quiet suburb of the Milky Way within the Orion Arm, about halfway between the crowded core and the empty fringe. We are far enough from the center to avoid the constant stellar bombardment, yet we are embedded in a region enriched with those crucial heavy elements from long-dead stars. This position grants us a stable orbital environment and the physical ingredients for a planet like Earth. This concept forces a staggering expansion of our perspective. We have been meticulously analyzing the conditions around individual stars, but now we must consider the character of the entire galactic neighborhood. When we discover one of those strange, challenging worlds, a super-Earth in the habitable zone of a red dwarf, or a potential Hycean planet, we must also ask where in its galaxy does it lie. Is it orbiting a star that itself circles in a calm, metal-rich spiral arm, or is it clinging to a sun that races through a more chaotic or impoverished region? Could complex life arise in a system that orbits close to the galactic core, if its planet had an extraordinarily thick atmosphere or a deeply buried biosphere to shield it from periodic radiation storms? Perhaps microbial life, tenacious and simple, could survive such episodic cataclysms only to be wiped out and forced to begin anew every few million years. Or maybe, in the outer reaches, a different kind of chemistry could compensate for a lack of certain elements, giving rise to a biology built from a simpler, more abundant palette. The galactic habitable zone is not a rigid fence, but a gradient of probability. It suggests that while life itself might be a possibility in many places, the long, uninterrupted stability required for life to evolve into complex, intelligent forms might be a privilege reserved for the quieter, richer suburbs of a galaxy. It adds another filter to the cosmic lottery, another reason why the silence of the cosmos might be so profound. Our search for life now spans an incredible hierarchy of scale, from the chemistry of a single droplet in an alien ocean, to the geology of an entire world, to the temperament of its star, and finally, to the majestic, swirling structure of its island universe. Each layer adds a note to the symphony of possibility, and our own existence seems to depend on a rare and beautiful harmony across them all. Detecting a biosignature would be a moment that shatters human history, but it also presents a dilemma with no precedent. The science of finding life is rapidly advancing, yet we have barely begun the conversation about what to do if we succeed. The instinct to reach out, to send a signal back toward that distant, promising world, is a powerful echo of our own curiosity. But this is not a simple hello across a crowded room. It is a shout across an abyss of time, space, and potentially of fundamental experience. Any life on a Hycean world or a tidally locked super-Earth has followed an evolutionary path divorced from every condition that shaped our own. Their perception of reality, their very experience of time if they are conscious at all, could be as alien as their planetary environment. A radio signal or a mathematical primer beamed from Earth might arrive as meaningless noise or worse, as a sudden, terrifying violation of a silent cosmos they have known for eons. This brings the fictional concept of a prime directive into stark, practical focus. It is a principle of non-interference, born from the recognition that an advanced civilization contacting a less developed one inevitably causes profound cultural and technological shock. Here, the potential shock is not merely cultural, but biological and existential. We must consider the risk of contamination in both directions. A future probe, even one designed with the utmost care, could carry hardy microbial stowaways from Earth into a fragile alien ecosystem, potentially acting as an invasive species that overwhelms native biology. Conversely, any sample returned to Earth could harbor unknown organisms with unpredictable effects. The protocol is not just about protecting them, but about protecting our own biosphere from unintended consequences. Beyond the biological, there is a deeper philosophical weight. A civilization evolving in the total isolation of a global ocean or beneath the unblinking eye of a red dwarf star has developed in a context of perfect cosmic solitude. Our sudden appearance in their sky or in their data streams would be an intervention of cosmic scale. It could disrupt their natural development, their myths, their science, and their sense of place in the universe in ways we cannot possibly predict. Is it our right to impose that awareness upon them, simply because we have the technological capability to do so? The question shifts from can we make contact to should we. This forces a necessary and urgent evolution in our planning. The scientific community is building the tools to detect life, but we must also build an international, multidisciplinary framework for how to respond. This framework must be rooted in caution, humility, and a profound respect for the autonomy of other worlds. It would involve ethicists, biologists, sociologists, and diplomats working alongside astronomers to establish guidelines for verification, for containment protocols, and for any potential communication. The decision to reach out cannot be made by a single nation or a private organization. It must be a considered choice for all of humanity, reflecting our highest principles of stewardship and respect. The greatest discovery we could make would not be a signal we send, but the wisdom to listen first, to learn without disturbing, and to recognize that some mysteries are best approached with silent awe. The map of the habitable zone is now filled with possibilities, yet it is the blank spaces that truly define the frontier. For every world we have theorized, a deeper mystery waits, a fundamental question that our current tools cannot yet answer. We have catalogued thousands of exoplanets, but we still do not know the most common blueprint for a living world in the Milky Way. Is the galaxy primarily a place of tranquil ocean planets under calm suns, or is it a domain of extreme, tidally locked worlds huddled around faint red dwarfs? Our own solar system offers no clue, as it contains neither a super-Earth nor a planet in a red dwarf's grip. We are trying to describe the forest while standing in a single, highly unusual clearing. Our understanding of planetary stability hinges on processes we cannot yet see from light years away. Take plate tectonics, the slow geological recycling program that helps regulate Earth's climate over eons. Is this churning of continents a universal requirement for long-term habitability, or just one way a planet can manage its atmosphere and temperature? And what of the super-Earths? Their immense gravity could suppress plate tectonics entirely, leading to a single, unbroken crust. Without this planetary thermostat, could such a world maintain a stable climate for billions of years, or is it destined for a more volatile fate? The answer lies buried beneath thousands of miles of rock on worlds we may never visit. Then there is the relentless fury of red dwarf stars. We know these flares can be devastating, but we do not know how often a planet's defenses prevail. How many of these close-orbiting worlds have managed to hold onto a substantial atmosphere against the constant stellar bombardment? Does a strong magnetic field guarantee protection, or can a thick, primordial atmosphere simply absorb the punishment? Each new observation of a red dwarf system is a test of planetary resilience, a clue to whether these most common stars in the galaxy are harbingers of life or sentinels of sterility. Even our most captivating hypotheses, like the Hycean world, rest on theoretical foundations. Can a deep, global ocean truly remain stable for eons under a crushing sky of hydrogen? Would the chemistry between that ocean and the atmosphere create a sustainable environment, or would it inevitably lead to a runaway greenhouse effect or a frozen, stagnant abyss? Our climate models can simulate these scenarios, but only direct evidence from a real world can confirm if such a beautiful alien habitat is more than just a compelling idea in a supercomputer. These questions all converge on the greatest unknown of all, the leap from chemistry to biology. Is life an inevitable chemical outcome on any world that provides liquid, energy, and persistence? Or is the spark that started the chain reaction on Earth a cosmic fluke of staggering improbability? Without a second example, we have no way to know. This is why the search within our own solar system is so critical. Finding even simple microbial life in the subsurface ocean of Europa or Enceladus would be a revolution. It would tell us that life can start independently in more than one place, transforming it from a miracle into a probable, perhaps common, feature of a universe rich in the right conditions. Ultimately, answering these profound questions will demand more than bigger telescopes. It may require a physical presence. The dream of an interstellar probe, a tiny craft sent to a nearby system like Proxima Centauri, is no longer pure science fiction. Such a mission could fly past a planet, sniffing its atmosphere and mapping its surface in detail, providing the ground truth that decades of remote observation cannot. It is a monumental challenge, but it represents the logical, perhaps inevitable, next step in a quest that began with a simple question: are we alone? The journey to understand these strange new worlds has just begun, and the most astonishing chapters, the ones that will rewrite the textbooks for good, are almost certainly still waiting to be discovered. Our voyage through the menagerie of habitable zone worlds reveals a universe far more imaginative and diverse than we ever dreamed. The search for another Earth has, paradoxically, led us to a profound duality. On one hand, it forces a deep appreciation for the delicate, intricate balance of our own pale blue dot. That specific recipe of a stable star, a large moon, plate tectonics, and a breathable atmosphere appears not as a universal standard, but as a rare and precious local masterpiece. We are not the model, we are the exquisite exception. Yet, this same search has utterly exploded the narrow confines of what the word habitable can mean. It is no longer a synonym for Earth-like. It is a spectrum, a grand declaration that life, if it exists, is a phenomenon of profound resilience and adaptability. From the crushing atmospheres of super-Earths to the eternal twilight of tidally locked planets, from the sunless abysses of Hycean worlds to the floating skies of puffy giants, each discovery is a lesson in cosmic humility. Nature's ingenuity far surpasses our own, crafting possibilities from a palette of physics and chemistry we are only beginning to appreciate. As our tools improve, from the James Webb Space Telescope to the coming generation of giant observatories, we stand on the brink of perhaps the greatest discovery in human history, evidence that we are not alone. But the data that finally arrives may not be a confirmation of our hopes, but a transcendence of them. That life may not look, live, or breathe anything like us. Its signature might be a strange chemical gradient in a hydrogen-rich sky, or an impossible imbalance of gases over a global lava sea. Let this knowledge fill you not with disappointment, but with a staggering awe for the boundless creativity of the cosmos. The universe is not obligated to recreate us. Its true masterpiece may be its infinite capacity for difference. The next time you look up at the stars, remember the new map we have drawn together. Out there are not just other Earths waiting to be found, but possibilities that still reside firmly in the realm of our wildest fiction. Oceans of methane, skies of molten salt, continents that do not exist, and biologies built on rules we have yet to write. The silence of the cosmos is not an emptiness but a canvas, and we are just beginning to perceive the first, faint strokes of a picture vaster than we ever imagined. If you found this journey as mind-expanding as we did, share your thoughts on which of these alien worlds fascinates you most in the comments below, and subscribe to continue exploring the universe's greatest mysteries with us.